Hi all. I don't have many of these papers in my channel yet because these papers are slightly different from the international A-level material. So these are the Edexcel exams from England, I believe. Okay, and these are at the advanced subsidiary level, and specifically this is paper 2 called Core Physics 2 from the UK, I believe. Let me know in the comments though. I've noticed that whenever I upload papers like this, the views go up a lot. So I assume there is a demand for this. Anyway, this is the paper from May 2024. My understanding is that these exams in England are taken only once per year. Again, let me know in the comments. The material is most similar to what will be the International A-Level Unit 2, okay, with the addition of lenses, okay? So lenses are only appearing in the UK curriculum, not in the international curriculum, but everything else is very similar to Unit 2. So guys from England, watch the international A-Level videos as well. I think they will be useful for you as well. So anyway, let's dive in. So section A is different from the section A of of international A levels, in that it's 8 multiple choice questions and I think 5 long writing questions or calculator problems, etc. And then section B is just 2 problems. Okay. Uh, the same things I say in my international A level videos apply here. If a question awards 10 marks, you should devote about 10 minutes to it. So a minute per mark. And the other thing I say is that whenever you try to solve a problem and it doesn't occur immediately during an exam, skip it. Try to solve the other problems, build momentum, and return, excuse me, return to the problem you didn't know how to solve in the end. Anyway, let's start. Question 1. The graph shows how the displacement of particles in a progressive wave varies with distance along the wave at a particular instant. Okay. Which of the following is the phase difference between the particles S and T? Okay, so you see that they are excuse me, half a wavelength apart, right? So a full wavelength is this one, right? So that's one wavelength. Since this is the displacement distance graph, I don't know why though that writing aids thing always appears anyway. Anyway, the quick way to figure this out is to write the phase difference is 2 pi over the wavelength times the distance between the 2 points, so delta x. Okay, so in this case delta x is lambda over 2, so we have the separation between the particles. This is what I was looking to find. Sorry guys. So 2 pi over lambda times lambda over 2. Lambda cancels, 2 cancels, and we are left with pi, which is option C. Moving on. Lenses. Okay, as I said, this is the only material in the UK curriculum that does not appear in the international curriculum. Everything else is the same. So 2 diverging lenses are combined as shown. The focal length of each lens is 0.2 meters. Which of the following is the total power of the combination? So let's find the power of one lens. So that's going to be minus, because it's a diverging lens, 1 over 0.2 meters, which gives us minus 5d. It's called diopter. In Greek, it will be dioptra. It's a Greek word, but I don't know how to pronounce it in English, so let me know. And anyway, since we have 2 such lenses in contact, the combination will give us a P total equal to 2P, since they are identical. So their power is minus 10D, which is option D. Okay. Question 3. An electron in an atom absorbs energy E and is excited from one energy level to the next. When the electron returns to its original energy level, a photon is emitted. okay? Which of the following is an expression for the wavelength of the emitted photon? So we have two energy levels, we have an electron that jumps to the next level, and it goes back by emitting a photon, okay? So we have HF for the photon, and the electron returns where it started, okay? So this energy difference is E, right? So E is going to be equal to just HF, right? And the frequency is equal to C over lambda. For any wave, the frequency is equal to the velocity of the wave over the wavelength, and for light, of course, the speed is c. Okay, so we only have to solve for lambda. So hc over e is the correct answer, which is option A. And here I want to pause and mention something I always mention in my international videos. Okay. Sometimes in these multiple choice questions, you can figure out the correct answer by inspection. Okay, so lambda has units of meters, right? H has units of joules times seconds, okay? C has units of meters per second, and energy has units of joules, right? So if we divide this, we see that we get units of meters, right? So combinations D and C do not yield dimensions of meters, right? So only options A and B can be correct. But then B is also, I mean, notice that B is actually 1 over meters, because in B, you have energy in the numerator, so joules in the numerator, and then in the denominator, you have units of joules times seconds, and then meters over seconds, okay? So you have units of 1 over meter. So this is an example in which you don't even need to know the physics of the problem, excuse me. You just need to work out the units to figure out that only A can work. All other options are wrong. Okay, so you arrive at the correct answer by eliminating all the wrong answers. Okay, so that's another technique you can use when you take papers. So let's move on. Question 4. The image formed by a lens can be described as real or virtual. Which row of the table describes a real image and a virtual image? Okay, so real images, actually let's use a clean page to show what's going on. So if these are the lenses, okay, and let's draw it like that. So we have an object. This is the focal length. Okay, so 1, 2, 3, 4, 5, 1, 2, 3, 4, 1, 2, 3, 4, 5. So that's F as well. So this will give us a real image. So if we have light rays that travel like this, okay, and there, and then this ray travels like that, okay. So this is the image, okay. So that's a real image, okay. And now let's do a virtual image. So in a virtual image, actually let's use the same diagram. So let's take an object and put it between the focal length and the lens. So something like that. So we have a light ray that goes like that and then passes through the focal length. Okay. And then we have to project it backwards, right? Okay. No, that's not it. So it needs to be a straight line. Okay, that maybe. And then you also have this light ray that goes through the focal length. Okay, that's not perfect, but that's a virtual image, okay? The bottom line is that virtual images, you cannot project them on a screen. They are larger than the object, and they are on the same side of the lens as the object. Whereas real images, you can project them on screens, they are inverted, and Yeah, the word cells. They are smaller than the object. Okay, so let's go read the options. Option A, real image formed on the same side of the lens as the object. That's wrong. Okay, B, can be produced on a screen. That's actually correct. And then let's read the virtual image formed on the same side of the lens as the object. So that's the correct answer. Okay. Now, option C, formed on the same, a real image is formed on the same side of the lens as the object. That's wrong again. And then a real image can be produced on a screen. That's option D. And then for the virtual image, they mentioned can be produced on a screen. So D is wrong. So again, this is an example of a question in which you can arrive at the correct answer by eliminating all the wrong answers. Okay, so B is the correct answer. All right, let's move on. Okay, question 5. The photoelectric effect provides evidence for the particle nature of electromagnetic radiation. Which of the following is not observed in the photoelectric effect? Excuse me. Okay, option A. Photoelectrons are released instantly. Okay. Wait, they are asking us for something that is not observed. So A is observed. Okay, I was confused for a moment. Then B, photoelectrons are only released above a certain frequency of radiation. That's true, and it is observed. C, the energy of the photoelectrons is determined by the intensity of the light. That's wrong. Okay. Only the number of photoelectrons is determined by the intensity. So, and then D, the energy of the photons is proportional to the frequency of radiation. That's true. Okay, so C is the correct answer. Okay, 6. Which of the following is the SI base unit for breaking stress? Okay, this is a trick question. Okay, let's see. So stress is force per cross-sectional area. And if we use the units, so square brackets means the units of a quantity. So the units for sigma are newtons per meter squared. And then you will be tempted to say, oh, that's pascals, which is kind of correct, but it's not the base unit. Okay. So it's a trick question, guys. Be careful. So what is a newton? A newton is given by kilograms meters over second squared and then over meter squared. So meters cancel. And we are left with option D because those are the base units. How did I know that newtons are kilograms times meters per second squared? Because F is equal to ma, and F, the force, is one of the derived units that have a name, okay? And the unit for force is newtons, right? And then mass is a base unit, kilograms, and then acceleration is given in meters per second squared. Okay, so that's how I know. All right. Question 7. I don't know why I keep saying option. Okay. Okay, question 7. A ball bearing with radius r falls through a fluid with density rho. Which of the following is an expression for the upthrust acting on the ball bearing? Okay, so upthrust is given by the density of the liquid fluid, right, times G times the volume of the ball bearing, okay? Because of course, rho times V is the mass of the displaced liquid, so M times G is the weight of the displaced liquid, okay? Anyway, so that's rho G times 4/3 pi r cubed. And this is option, which one is it? 4 pi r thirds. Okay, that's option B. Okay, and again, you can see that option A is wrong. Oops, sorry. So option A is wrong. So is option C and option D. Okay, so again, you see that by demanding that this quantity has units of newtons, only option B can work. Okay. 8. Unpolarized light passes through two polarizing filters as shown. The planes of polarization of the two filters are parallel. One filter is rotated so that the planes of polarization of the two filters are perpendicular. Which of the following describes the change to the intensity of the transmitted light. There will be no transmitted light because if they are perpendicular, so let's say they are like that and like that, then you will have waves that oscillate in this plane passing through the first filter, and then of course they cannot pass through the second filter. So the intensity will be 0, so option B. Okay. So this was the multiple choice section. Let's move on to the next question, okay, which is not multiple choice. Okay, question 9. A telescope is used to produce the magnified image of a full moon. The telescope consists of two converging lenses, okay, the objective lens, this one, okay, and the eyepiece lens as shown, okay. Let me know in the comments if you ever looked through a telescope. I looked through a telescope just once in my life, which is embarrassing for a physicist. But anyway, the objective lens produces an inverted image at point X. The image at point X is the object for the eyepiece lens. The eyepiece lens produces a magnified image. Okay, question A, the power of the objective lens is 0.8 D. Calculate the distance of the image X from the objective lens. Okay, so we are given the power of the objective lens, which you can use to find the focal length. So P is 1 over F, so F is 1 over P, so 1 over 0.8 D, which yields 1.25 meters. Okay, so the object in this case is the moon, right? So we have to apply 1 over U plus 1 over V equals to 1 over F. U is infinity, okay, because it's the moon. So it's really far away, so we can practically, like, the way I think about this, which is kind of silly, but it works in physics at least, not in math. No, it works in math as well. So if we have 1 over something, so 1 over x, so if x is 100, that's immediately 1 over 100, which is 0.01. If x is 10,000, right, we will have 0.000. Do I have enough zeros? I do, right? Yeah, 0.0001. Now, if I have 1 over a billion, that's practically 0. Okay, so the moon being, let me know the distance, the actual distance in the comments, but I think it's about 300,000 kilometers away. So 1 over that is 0, okay? So U is infinity, so we just have to say 1 over infinity plus 1 over V is 1 over F, that's 0, which means that V is F equal to 1.25 meters away. So the image is 1.25 meters away from the objective lens. Simple. Okay. B. Complete the ray diagram to scale to determine the magnification of the image formed by the eyepiece lens. Okay. So this is to scale, so we'll have to measure this distance. But let's do the ray diagram first. So we will have a ray. Actually, let's use a different color. We will have a ray that goes towards the lenses like that, and then passes through the focal point. No, that's not what I want. I don't want a line that bends. So let's do that. Okay, great. That's my first ray. And then the second ray, and we have to extend this, I guess, on this side. Okay, so that looks good, I think. And now this looks okay. Then we have to extend. So let's see. So yeah, that looks okay-ish. So this is our virtual image. Okay. So, what's the question? Determine the magnification. Okay, so the magnification is U over V. Okay, so this will be V, and this will be U. Okay, let's bring up the ruler. Okay, I really hated using this instrument, but anyway, okay. So that's what, 1, 2, 3 centimeters, right? Is it 3? Yeah, it's 3. So U is 3 centimeters. And now, okay, let's make this 0 to measure the other one. So 5, 6, 7.5, something like that. It's actually V over U. Okay. Sorry, guys, for the confusion. V over U. Okay. So we said that, U is 3. Okay, so that's the denominator, and the numerator is 7.5, right? So this gets deleted. So we get 2.5, which is actually minus 2.5 because it's a virtual image. Okay, so this was question 9. Okay, question 10. Scientists can use a pulse echo technique with ultrasound to detect plastic in the oceans. First time I'm hearing about this. A transducer that emits and detects ultrasound pulses is positioned just below the surface of the water. Question A, an ultrasound pulse was transmitted. The pulse was reflected from a piece of plastic under the surface, and the pulse was detected 4.1 milliseconds later. Calculate the distance between the plastic and the transducer. The speed of sound in salt water is 1500 meters per second. Okay, so the distance travel is going to be V times T, but we need to divide by 2 because it has to go back and forth. It's a pulse, right? So we have 1500 times 4.1 times 10 to the negative 3 seconds over 2 yields 3.08 meters, so about 3.1 meters. Give a reason, this part B, why the ultrasound is emitted in short pulses. So the answer is that the reflected pulse, actually, so that the reflected pulse, so that the reflected pulse returns to the transducer before the next pulse is transmitted. Excuse me, I ran out of space. I should have used a clean page, but anyway. Part C, explain why small pieces of plastic are more likely to be detected by using ultrasound with a high frequency. Okay, so shorter lambda, high frequency means shorter lambda. I have to mention this. So, okay, let's write that V is lambda times the frequency, right? So lambda is V over F. So if F increases, lambda decreases, okay? Now a shorter lambda diffracts less around small objects, so the signal reflects back rather than bending around objects. Okay, does this make sense? I mean, if it's a very small piece of plastic, if you have a large wavelength, it's going to diffract around it and it's not going to get reflected. Whereas if it's a very high frequency ultrasound, it's going to have a very short wavelength and it's just going to hit the object and return. Okay, it's not going to diffract at all. Okay, this was question 10. Let's move on to question 11. Okay, a technician shone light from a laser through a diffraction grating. A pattern was observed on a screen 4 meters away. The pattern consisted of 5 maxima as shown. The diffraction grating has 4 times 10 to the second lines per millimeter. Question A. The technician wanted to check that the wavelength emitted by the laser was within the range 450 nanometers plus or minus 10 nanometers. She measured the distance between the two second order maxima as 3.25 meters. Deduce whether the light from the laser was within the range 450 plus or minus 10 nanometers. Okay, so first of all, let's find D, okay? We have 400 lines per millimeters, right? So D is 1 over 400 lines per millimeter. So we need 10 to the negative 3 over 400, which means that D is 2.5 times 10 to the negative 6 meters. Now, we can also figure out, they tell us that this is 4 meters away and that this is 3.25 meters away. So we can find theta, right, for the second order maximum. So tangent of theta is 3.25 over 2, right? And then over 4 meters. So this is 0.41, which means that theta is 22.11 degrees. Okay, let's start a new page. So we also know that d sine theta is n lambda. So all we have to do is to solve for lambda. So lambda is d sine theta over n, and we have everything now, right? So d is 2.5 times 10 to the negative 6. Then we need to multiply by the sine of 22.11 degrees, and then divide by 2 to find 470.5 nanometers, which is larger than 450 plus 10 nanometers. So it doesn't work, okay? So so the light was not, so light was not within the range. Okay, question B. The electrons in an electron beam have a speed of approximately 10% of the speed of light. Is it possible? It is possible, to demonstrate diffraction with this electron beam when the electron beam is incident on a graphite target. If the spacing of the atoms in the graphite target were equal to the spacing of the lines on the diffraction grating used by the technician, this electron beam would not show diffraction effects. Explain why. Your answer should include calculations. Okay, so the calculation we can do is to find the wavelength of these electrons. Okay, so we can do so using the Broglie's, Prince de Broglie's wavelength formula. So the wavelength of the electrons is h over their momentum, which is equal to h over their mass times their momentum. So it's h over the mass of an electron times 0.1 c, which is 10% the speed of light. If we plug in numbers, we find 6.63 times 10 to the negative 34 over 9.11 times 10 to the negative 31 times 0.1 times 3 times 10 to the 8. And I forgot to include the units. So joules times seconds for h, kilograms for the electron mass, and then meters per second for the speed of light. So this ends up being, okay, let me think. So 2.43 times 10 to the negative 11, 1 joule is 1 kilogram times meter squared over second squared, and then we have second squared, kilograms, meters, so kilograms cancel. So everything cancels except meters, okay? But 2.43 times 10 to the negative 11 meters is much smaller than, what was the value of D from before, than 2.5 times 10 to the negative 6 meters, so no diffraction. So no diffraction. So if you use the diffraction grating with these electrons, you will observe nothing. Electrons will just go through. Okay, this was question 11. A student investigated the properties of metal wires. Question A, describe how the student should determine the diameter of a wire. So use a micrometer or digital calibers. So a micrometer or digital calibers to measure the diameter. That's the first step. The second thing you need to do is to repeat measurements, and take the mean of your measurements. And most importantly, take measurements at different positions. This looks like a Greek sigma. I don't know why this happened. So take measurements at different orientations and positions along the wire. So the wire will look like this, right? Cylindrical and long. So I mean, you should take measurements here, here, and here. And as far as the diameter goes, you should test different orientations like that, okay? So that's the answer. Let's move on to part B. The student applied increasing force F and determined the corresponding extension delta X of the wire. The force was applied in increments of 5 newtons up to a maximum value of 40 newtons. The student plotted a graph of F against delta X as shown. The Young modulus E of the material of the wire is given by the expression gradient times the length of the wire over A, where A is the cross-sectional area of the wire and X is the original length. Okay. Derive this expression. So how are we going to go about this? So stress is strain times the Young's modulus, right? But stress is force per cross-sectional area. Strain is X. Delta X, the extension over X, is strain times E, okay? So if we plot F versus delta X, let's do that. It will look like F is E times A over X, times delta X. This is a straight line with gradient equal to E times A over X, which means that the Young's modulus is the gradient times, X over A, right? So that's the proof. Let's move on to part 2. The values of the Young modulus for some metals are shown, okay? Deduce which metal the student's wire was made from. Okay, so first of all, let's find the gradient, which is delta F over delta X, okay? So you can choose any 2 points you want. I chose here, the point at 30. Okay, so delta F is this. and delta x is that. Okay, so I chose the origin and that point over there. So delta f in my case was 30, and if you measure this distance is 6.3 millimeters. Okay, so 6.3 times 10 to the negative 3. This is newtons per meter. So this is 4,761.9 newtons over meter. So the Young's modulus is equal to the gradient, which is the value you just found, and then newtons over meter again. When I plug in numbers to expressions, I put all the units to the right and all the numbers to the left. It's kind of convenient. The length is 3 meters, and the cross-sectional area is 1.14 times 10 to the negative 7 meters squared. Okay, and this ratio yields 125.3 gigapascals, which is copper, close to copper. Okay, it's not exactly it, but it's the closest. So this is made of copper. Okay. 3. The student repeated measurements of force and extension using a thinner wire of the same metal and length. He changed the values of the force he applied to the wire. Explain 2 changes that the student should make to the values of the force he applied to the wire. So use a smaller maximum force, okay, because a thinner wire has a lower breaking stress. Okay. Breaking, stress force, okay, and will exceed the limit of proportionality at a lower load. Okay, so and the limit of proportionality, if we use this graph, is let's use purple. So maybe this point over there where it starts bending. Okay, so that's the limit of proportionality, because below that you have a linear relationship. Okay. Okay, let's move on. We have to provide a second point, and the second point is that you should use smaller increments, okay, in force. Oops. So that enough data are collected in the elastic region before the limit of proportionality is reached. Okay, so these are the 2 things you should change with a thinner wire, because it breaks faster, at a lower load. Okay, so this was question 12. Let's move on to the next one. Okay, question 13 is the last one in section A. Okay, so when an object moves through a fluid, Stokes' law may apply. State 2 conditions that determine whether Stokes' law applies at a moving object. So object must be small and spherical. Okay, and the second point is that object must be moving at slow speed, and flow must be laminar. Okay, B. A teacher demonstrated the viscosity of fluids using a falling ball method. The teacher released the ball bearing at the surface of a tall column of a viscous fluid. The teacher repeated the demonstration using an identical ball bearing falling through a fluid with a higher viscosity. Explain the motion of the 2 balls, of the 2 ball bearings as they fell. Okay, so, initially, this is a 6-mark question, a star question, which means that it's a long writing, and it awards 6 marks. So you should provide about 5 to 7 sentences that describe the situation. So initially, weight is larger than upthrust, so there is a net. Sigma F total force downwards, okay, on the ball bearing. Okay, second point, the ball bearing thus accelerates down due to that total force, okay? So as V increases, the drag, the viscous drag increases, okay? Because remember that the drag is 6 pi r eta and then V. So as V increases, the drag increases, okay? So the drag force at any given speed is greater in the fluid, in the fluid with higher viscosity eta, okay? Eventually, the upthrust plus the drag experienced by the ball bearing, and remember that if a ball bearing falls, it will experience its weight, an upthrust, and a drag force, right? So eventually the upthrust plus drag equal weight. So sigma f is 0. So acceleration is 0. And ball reaches V terminal, the terminal velocity, okay? So the ball in the more viscous fluid reaches terminal velocity faster. So reaches V terminal at a lower speed. And this is a consequence of this formula we've written down a little bit earlier. So if the viscosity eta is higher, this drag force is going to be higher, so it's not going to reach a very high terminal velocity, okay? So this was part B. Moving on to part C. The ball bearing fell at a terminal velocity through the fluid. The ball bearing fell 0.75 meters in a time of 3.4 seconds. And they give you the viscosity and the radius of the ball bearing. Calculate the viscous drag force on the ball bearing. Okay, so first of all, let's find the V terminal, which is of course 0.75 over 3.4 or 0.22 meters per second. Then the Stokes force is 6 pi eta r V. So it's 6 pi, and then the viscosity is 1.8, excuse me, times the radius, which is 5 times 10 to the negative 3, times 0.22, and this yields 0.037 newtons, okay? Now, part 2, a student considers what will happen if the temperature of the liquid increases. The student writes the following statement: when the temperature of the liquid increases, the viscosity decreases, which is correct. Therefore, when the ball bearing is falling at terminal velocity, the viscous drag force will be less. Assess the validity, of the student's statement. So, the first observation is that at V terminal, okay, the drag plus upthrust equal the weight, okay? So you can solve for the drag force, which is weight minus upthrust, okay? But upthrust and weight do not depend on temperature, okay? So weight minus upthrust is unchanged at V terminal, okay? So student is wrong, actually, surprisingly. And he or she is wrong just because the ball bearing is already falling at V terminal. Okay, so everything is said and done somehow. So the weight minus the upthrust is going to remain constant. So the viscous drag will not reduce. Okay. Okay, section B. It says answer all questions in the spaces provided. There are just two questions in section B. So it's slightly different than the international A levels. Okay, read the extract and answer the questions that follow. Scientists have observed small dust particles jumping above the moon's surface. Small particles on the surface of the moon acquire a charge due to the photoelectric effect caused by incident UV radiation from the sun. Electrostatic forces between charged dust particles cause these particles to move. It is believed this is a mechanism by which dust particles can be transported across vast regions of the moon. I actually did know that, and the reason is that on the moon doesn't have an atmosphere, right? So particles from the sun directly hit in, they land on the surface of the moon easily. And lots of those particles are helium-3 particles, which are believed to be valuable for nuclear fusion. So if we ever manage to make fusion at an industrial level, okay, we will need lots of helium-3, and will be mining of the moon for that, okay. I don't know if this is related to the recent Artemis missions, because I know I have not a friend, maybe an acquaintance who works at NIF. Okay, I think it's called NIF, National Ignition Facility. It's in California, and they study nuclear fusion using really powerful lasers that kind of bring together a nuclei until they fuse. So recently they were able to extract more energy out than what they put in, but for a few, I don't know, microseconds or something like that. I don't know the details because I didn't read about it too much. But anyway, so if this ever happens, we will need lots of helium-3, and the moon will be the next I guess, stage for future wars or something. I don't know how this is gonna play out, but you get the idea. There is also a movie called Moon from 2009, I think, that kind of discusses these kind of things. So anyway, so question A: explain how the incident UV radiation causes dust particles to become charged by the photoelectric effect. So 3 marks. So we have to provide about 3 sentences. So electrons in dust particles absorb the UV energy. Okay. Absorb the UV energy from photons. Okay. One photon interacts with one electron only. Okay, so electrons are released from the surface of dust particles. Okay, leaving the particles positively charged. Okay, so that's the answer. Okay, B. The angle at which the UV radiation is incident on the moon varies across its surface as shown. The number of dust particles per unit area that becomes charged is greater where the UV radiation is incident on the moon's surface at 90 degrees. Explain why. So this is similar to the Earth. Like the equator heats up faster because the rays kind of hit the surface directly. So, I mean, it's perpendicular there, whereas here the rays are not really perpendicular, okay? So they fall at an angle. So that's the explanation. So at 90 degrees, like here in the middle, right? At 90 degrees, UV radiation is spread over a smaller surface area. Okay, so there are more incident photons per square meter per seconds. Okay, so more electrons absorb UV radiation and are released. I hope this makes sense. If it doesn't, ask me a question and I will try to write an answer. Okay, move on. Part C. The work functions of some minerals, that have been found on the surface of the moon are shown. UV radiation with a frequency of 2 times 10 to the 15 hertz is incident on a sample of one of these minerals, and electrons are emitted by means of the photoelectric effect. The released electrons have a maximum kinetic energy of 4 electron volts. Deduce the mineral from which the photoelectron is released. Okay. H times the frequency of the photon goes into the work function plus the maximum kinetic energy of one electron. Okay, so the work function is HF minus KE max. Okay, so this is equal to 6.63 times 10 to the negative 34 times 2 times 10 to the 15 hertz, which is the frequency. And then we divide by 1.6 times 10 to the negative 19 to convert to electron volts. So the units for the Planck's constant are joules times seconds. This is given in hertz, so seconds. And then this quantity down here is joules per electron volt. So you see that everything works out. Okay. And then we have to subtract 4 electron volts for the kinetic energy of the photoelectron. This yields 4.29 electron volts, which is about 4.3 electron volts. So it's this mineral called ilmenite. I don't know. Let me know in the comments. Never heard of it before. Okay. Let's move on to part D. The motion of a charged dust particle on the moon is influenced by the nearby charged dust particles as well as the moon's gravity. The lack of an atmosphere on the moon means that the dust particles experience no resistive forces. A particular dust particle experiences an electrostatic force of 8.2 times 10 to the negative 17 newtons that is perpendicular to the gravitational force. The magnitude of the resultant force on the particle is 8.7 times 10 to the negative 17 newtons. Calculate the magnitude and direction of the acceleration of the particle, and they give you the gravitational field strength on the moon and the weight of the dust particle. Okay, so first of all, weight is mass times g. So mass is weight over g. So 3 times 10 to the negative 17 newtons over 1.6 yields 1.875 times 10 to the negative 17 kilograms. Now the acceleration is force per mass, right? And the total force is given as, or the resultant force is given as 8.7 times 10 to the negative 17, and then the mass is 1.875 times 10 to the negative 17. So this yields 4.64 meters per second square. Okay. So we have to find the magnitude and direction of the acceleration of the particle. Okay, so we found the magnitude. Now the acceleration, we are given that there is a force to the right, 8.10 times 10 to the negative 17 for the, and this is the, the electrostatic force. And then the resultant force has magnitude 8.7 times 10 to the negative 17. So we can find the angle with respect to the vertical, okay? So sine theta is 8.2 times 10 to the negative 17, which is this side, right? Which is the same as that side, over the hypotenuse, which is 8.7 times 10 to the negative 17, yields 0.94. So theta is 70.48 degrees. Okay, so this was question 14, and we are ready for the last problem in this section B of this paper. Okay, so let's start. Okay, question 15. A rain sensor is mounted on the inside of a car windscreen. When the rain sensor detects raindrops on the windscreen, a motor is switched on to operate the windscreen wipers. Part A, the rain sensor consists of a series of infrared emitters and detectors. Infrared rays are emitted from a sensor, travel through the glass windscreen and are incident on the outside surface. A ray is incident on the boundary between the glass and a raindrop as shown. Okay, the angle of incidence I is 45 degrees. Determine what happens to the ray at this boundary. Okay, let's just use Snell's law. So the index of refraction of glass times sine of the incident angle is going to be the index of refraction of water times sine of theta. And this is going to be larger than, so it's going to be something like, it's going to bend away from the normal. So something like this. Okay, so that's going to be theta. And the reason why it bends away from the normal is that we go from an optically denser material, which is glass, to water, which is optically thinner material. So sine theta is 1.5 times sine of 45 over 1.3. Sine of 45 is equal to the cosine of 45, equals to square root of 2 over 2. It's one of the few ones that I remember by heart, okay? So that's 0.88. And of course, the tangent of 45 is what, guys? Pause the video and let me know in the comments. So it's 1, right? Okay, so theta is 54.68. So the math work out. I mean, we see that theta is larger than the incident angle as expected. Okay, moving on. Part B. A student modeled a simple infrared detector using a light-dependent resistor, LDR, in series with a variable resistor, R. She connected the motor in parallel with the LDR as shown. Okay, the intensity of the light incident on the LDR increased. Explain what happened to the speed of the motor. Your answer should include reference to conduction electrons. So you have to remember that LDRs, diodes, solar panels are semiconducting materials. And in these materials, if you give them heat or photons or whatever, you increase the number of electrons in their conduction band, as it is called. So their resistance drops. Okay, so more light means more conduction electrons. So more conduction electrons in the LDR. Okay, so the resistance of the LDR decreases. Okay, the ratio of the resistance of the LDR over R total, where R total is R plus R LDR, decreases. So the potential difference across the LDR and the motor decreases. Okay, so this means that motor receives less potential difference, so its speed decreases. And that's the answer. Okay, part 2. The power supply consisted of several 1.5 volt cells in series. The students set the resistance of resistor R to 270 ohms and measured the potential difference across the motor as 5 volts. In this situation, the resistance of the LDR was 193 ohms. The motor had a very high resistance. Deduce the number of cells the student used. Okay, so the potential difference across the motor is equal to the resistance of the LDR over R of LDR plus R times V. Okay, so 5 volts is the potential difference across the resistor, and then we have 193 over 463 times the voltage of the cells. Okay, so the voltage of the cells end up being 11.99 volts. Okay, so it's approximately 12 volts, which is 8 times 1.5, okay, volts. So 8 cells were used. Okay, so this was paper 2, core physics 2 from the UK curriculum. I hope these videos are useful. Guys, I'm kind of sloppy about this, but I have many videos in my channel, okay? So for those of you who are taking these tests, the International Unit 2 papers will be useful probably. And I have other paper 2 videos as well. So again, I'm not making this for a living yet. I hope one day I will. So the channel is still very young. It's growing very slowly. So if I become able to do this full time, I will upload as many videos as I can because I kind of enjoy doing this. But it takes time, guys, and I have other things to take care of. So I will upload the next video once I have time. Please like and subscribe. And yeah, if anything's wrong with the videos or you have questions, let me know in the comments. See you in the next one. Bye.